So, we are talking about rainfall runoff modeling, as you may remember, and in particular up to now we talked about the rational formula. I get the PowerPoint presentation so I can just show you where we are. Here it is, just 1 second. Okay, here we are. And so this is the rational formula. I told you that there are some more details on the web pages, but I don't think you need to learn much more about this. And keep in mind the concept, which is essential, namely the fact that this is an empirical formula that anyway satisfies the physical laws governing the process, and in particular it satisfies the mass balance equation, and you can clearly recognize mass balance there, and you can clearly recognize, not clearly, you can also recognize the principle of conservation of energy, which is taken into account in an implicit way, because I mentioned to you that we need to define the duration of the rainfall, which has to appear there, and the duration of the rainfall is defined in a way that takes into account the principle of conservation of energy. What I wanted to tell you is that this is a first, very basic example of rainfall runoff model, which was conceived, you may remember, as a flood model. Namely, it's a model that was conceived to provide an estimate of the peak flow of the hydrograph. Okay, keep in mind that for doing this, we introduced the definition of a reference river cross section, where we want to compute the peak flow. So there is the river cross section that we defined in the first lecture, I think, or second. And we define what is the catchment. We also define what is the concentration time. So please remember these three definitions, which are recalled in my web pages, and there are links, Wikipedia links, to illustrate these definitions. These are definitions, I know that definitions are boring, but in this case they are instrumental, they are fundamental in order to understand the problem. As I said, this is a model for estimating the peak flow. It's typically called an event-based model. Event-based model. What does this mean? It means that it's conceived for simulating just one event, an event of rainfall and subsequent runoff. And given that this is a peak flow model, the event that is simulated by this model is a peak flow, let's say a flood event. Not necessarily a flood. I say flood in order because I think it's clearer. So it's a single event, an extreme event that may originate a flood, and the model is conceived for simulating just that. There is another category of models that don't simulate just a single event, but simulate the rainfall runoff transformation long time for a whatever long time. And these are called the counterpart of event-based models. They are called continuous simulation model. So what is the difference between event-based models and continuous simulation models? The difference is that, again, it's the simulation time. The event-based model, the simulation time is limited to one event, and the continuous, why they say continuous? Continuous not intended as a mathematical concept like continuous as opposed to discrete. Continuous means long time in this case, okay? So in mathematics we distinguish between continuous function and discrete functions, and the difference is that the discrete functions are point functions. In this case, continuous means long time, continuated in time, okay? We are not strictly interested in flood models in this course because we are interested in water resources management, and typically floods don't serve much in terms of water resources management. They occur when there is plenty of water. They cause also surface runoff that typically cannot be used immediately because there is suspended material, there is turbidity. We are interested in water resources management in low flows rather than high flows. And low flows typically occur not inside an event of rainfall runoff. They occur in the tail, in the long tail of an event, rainfall runoff. So we need a continuous simulation for simulating low flows. Low flows take place in the long time. Low flows are not occurring typically within a couple of days. They occur typically within a season or within a drought, and the drought is a long time process. The flood is it's a very impulsive event. It typically occurs in a short time. The drought is different time scale, it's longer. So in this case, the classification of rainfall runoff models in these two categories helps us in understanding what is the type of model we are interested in. Helps us in understanding that why the rational formula is not so relevant for us. So this is why classifications are sometimes useful. Again, as I already told you, don't interpret this classification as rigid. There are models that may fall in both categories. And the rational formula typically not, because it's not a continuous simulation model. And look for the physical reason why the rational formula cannot be a continuous simulation model. And the reason is that the rational formula doesn't take into account some phenomena which are very important during low flows. For instance, evaporation. Yes, you may say that it's taken into account here in the coefficient C, but actually it's a very rough way of taking into account evaporation. Evaporation is extremely important, again, for governing low flows, and here it's not well described. Also here, there is an important part of the process that is not described. Storage. Storage is not there. The catchment is able to store water. Here you see only a transfer. I have an input and an output. Storage is not taken into account. And again, storage is extremely important, especially for low flows. Low flows are originated by storage that was accumulated into the catchment. Water volume that was accumulated into the catchment, and it's given back in the long term. Typically, storage is a long process. It's a process that evolves in time in a slow fashion. Here it's not taken into account. I just wanted to say that there are other classifications of rainfall runoff models, and we don't need to know all of them. There are some examples of classification on my web pages, There is another classification that I want to mention to you because it's useful for paving the way to my next 40 minutes of lecture. And the second classification I want to mention to you is that divides the models again into two categories. And these two categories are lumped models and the counterpart is spatially distributed models. What's the difference? First, let me say that the rational formula is a lumped model. Lumped because the catchment is considered as a lumped entity, is considered as a whole, as a unique entity. Lumped means concentrated. And here you see that you just see, as an output of this model, the river flow and the considered river cross-section. You don't know anything of what happens in each location of the catchment. So you know the river flow just at the closure. Okay? And you just refer to here. You consider the rainfall, which is called there E, has uniformly, as we discussed, distributed over the catchment. You don't take into account the reality that rainfall may be higher in the mountains, lower in the lowlands, etc. You just consider rainfall with one value, like it is homogeneous over the catchment, spatially homogeneous. Actually, as I said, the reality is different. Over a catchment, especially if it's large, you may have heavy rainfall here, low rainfall there, and we need for some application to consider this spatial variability. So in order to consider spatial variability inside the catchment, we apply another category of models, which is called spatially distributed. And the term gives the idea. Spatially distributed means that we look at the spatial distribution. So the catchment is not considered as a lumped entity. We look at the spatial distribution. Of course, you understand that the model becomes more complicated. The model is able to give you additional information that related to the spatial distribution, so it becomes complicated. But let's say for now that the rational formula is a lumped model. But it's important that you start recognizing these terms. So when one talks to you about spatial variability, spatial distribution, you know that you have to call into play a different category of models. Okay, let's now move forward and let's move into our interest, into our job. So if the rational formula is an event-based model and a lumped model, and I said that we need a continuous simulation model or a model that, you know, is prone to continuous simulation applications. Now let's move one step forward. And the step that I want to move forward is that related to the linear reservoir model. Some of you already know how the linear reservoir works, but I think it is extremely helpful if I dedicate 10 minutes to remind you how it works, because it is the basis for the next one. We will take into account and we will discuss two more models, two more rainfall runoff models. The next one, in order to better understand the next one, it's important that you have a clear perception and that I refresh you about how the linear reservoir works. Okay, the linear reservoir assimilates the catchment don't look at the slide. It's just for me because not look at the blackboard, but it's just for me not to forget. And then, of course, you may look at the slide and the web pages, but not for now, look at the blackboard. The linear reservoir is based on a conceptual representation. What does it mean, conceptual? Conceptual means that we use a concept, we use an analytical structure for the model that is derived from a concept. What I said until now is not clear. What is the concept that we use here? We assimilate the catchment to a tank. So this is a kind of schematization that is not really physically based. Because you understand, a catchment is not a tank. So if we assume that the catchment works as a tank, it means that we want to apply to the catchment the physics of a tank, which is not the same as the physics of the catchment. And therefore, this assimilation, this assumption that we make is called a conceptual assumption, because we use this concept that the catchment is like a tank. Okay, so let's assimilate the catchment to a tank. The tank is here. The tank has a water content that it's varying in time, and we call it WT. The tank receives rainfall. Let me see, I think I use, P. Rainfall, I call it PT, and releases a discharge, a bottom discharge, QT. Okay, this is rainfall intensity again. So if I look at the units of PT, it's a length over time. Just in order to make clear what kind of rainfall, because when we talk about rainfall, we always have to say if we mean a rainfall depth or a rainfall intensity. Depth is a length, the unit is a length. Rainfall intensity, the unit is length divided by time. Okay. Look, by assimilating the catchment to a tank, I am allowed to say that the tank has a storage, and this is a first step forward with respect to the rational formula. There is a storage into the catchment. Okay, now I can apply to this tank the continuity equation. Okay, let me write it. I can write that the difference between rainfall minus bottom discharge is equivalent to the derivative of the storage with respect to time. Look, here we have two options. In order, if I want to subtract from rainfall the river flow, I have two options here. They have to be expressed with the same units. So either I assume that the river flow, the bottom discharge, is expressed per unit area of the catchment, and therefore you know that the discharge, the unit is volume divided by time. But if I express it for unit area, it becomes a length by time, over time. Or the second option is that I put here not just the rainfall intensity, but the volume of rainfall over time, and this is what we usually do. Okay, so this P is expressed in length cube divided by time, because it's a PT that you can express in this way, is equal to IT times A. IT is the rainfall intensity that we used in the rational formula. In fact, in the rational formula, the rainfall intensity is multiplied by the area of the catchment. Okay, here you can say that rainfall that we denote with the symbol P is rainfall volume over time. And this is why I use two different symbols. in the linear reservoir and in the rational formula. So keep in mind, usually we use this approach in order to obtain from the bottom discharge the whole river flow, not the river flow, not just the river flow per unit area. Everything is clear? Okay. So if everything is clear, let me remove, the blackboard is small, let me remove this. I wait a bit. If I go too fast, you have to tell me, okay? And I can understand from your face and your movement of the hands, but please help me. Good. So let me remove this. Now it's clear for everybody that P is volume of rainfall over time. Okay? So this is the continuity equation. It's mass balance equation. The difference between rainfall and output from this tank, the difference between input and output is equivalent to the change in storage per unit time. And keep in mind here the derivative is total, and it's total because the only independent variable here is time. Or let's say, the variable only depend over time, this is correct. They don't depend on space in particular. Why is that? Because this is again a lumped model. The catchment is lumped in the conceptual representation as a tank, So the location is just the closure, and it's implicitly included here. There is no spatial variability. And therefore, if there is not spatial variability, variables only depend on time. So the derivative is total. And I suggest you to get used to recognize what's the difference between a partial derivative, a total derivative. Partial derivative, it means that you are taking the derivative over a coordinate, which is not the only one. Along a coordinate that is not the only one. Here you see that the derivative with respect to time is total, so you understand that this is the only coordinate, temporal coordinate that we are considering. There are no spatial coordinates. Okay, now look at the unknowns here. So rainfall must be known because it's observed. It's something that it's an input variable. What is the output variable? The output variable is Q. Good. But there is also W. W is varying time, and we don't know it. What is that? It's a state variable, clearly. It describes the state of the system. So we have two unknowns here. And two unknowns, it means that we have to find out another equation. Okay, so what is the second equation in the linear reservoir? The linear reservoir assumes that, and look, let me make a premise. The second equation must be expressed in terms of the same variables. So if I have two unknowns, the second equation must be expressed in terms of the two unknowns. Either has a link between the two, or has an external equation that gives to me information on one of the two. The second equation that is considered by the linear reservoir simply says that the bottom discharge, which is one of our unknown, is a linear function of the storage, which is the second unknown. So I can say that it's equal to Qt Wt over K. So this is a link between the two unknowns. It's perfectly fine, this second equation. It's empirical. It's just an assumption. Take it as an assumption by the linear reservoir, linearity between storage and outflow. So these are my two equations. Now the problem can be solved. Of course, you see that one of the two equations is a differential equation, and therefore I need an integration somewhere. Look, this second equation, I said it's an assumption. Is it reasonable or not? Is it reasonable that the discharge from a catchment is linearly related to storage? So if you want to understand whether it's reasonable or not, you have to think again the physics of the process. And in particular, the physics of the process suggests to me that I already considered the mass balance equation. There must be some energy balance into this model. So, of course, the second equation that I am introducing must be related in some way to energy balance, which is indeed the case here, because we are relating outflow from storage. And what is the relationship between storage, which is potential energy, and outflow, which is something more dynamic with some kinetic? It's an energy transformation. There must be an energy transformation there. And in fact, we can think, if we look at our conceptual scheme, we know that there is a relationship that is suggested by fluid mechanics that relates for a tank. For a tank, it relates storage with a bottom discharge. And this law is the Torricelli's law. Torricelli's law. Torricelli's law can be derived from energy balance. It says that Qt can be expressed in this way. Qt is equal to, this is Torricelli's law, to the velocity of the flow from the bottom discharge, so let me call it Vt, times the area of the hole of the bottom discharge. Let's call it not with A, but let's call it as V. And there is a coefficient that is very close to 1. This is Torricelli's law. Sorry. Actually, okay, and what is, in Torricelli's law, the expression for velocity? We know that velocity in Torricelli's law, and let me write it here, Wt is proportional to Wt squared. Or let me, sorry, it's proportional to Wt square root. There is a proportionality. I'm not going into the details. And the proportional, the constant of it's 2g. Okay? But let's forget the details. We just know that velocity is proportional to the square root of storage. So, from this relationship, we see that there is no linear relationship between storage and outflow in a tank. The relationship is non-linear. Remember the definition of linearity, and please try. You see that if there is a quadratic dependence, quadratic or dependence through an exponent that is not 1, and there is a square root, the exponent of W is 0.5, of course it's not linear. So this assumption that we make here is an assumption that is related to the physical law governing the process, but it's an assumption that actually in a tank wouldn't be satisfied. Whether or not it's satisfied in a catchment, it depends on the catchment. There are some catchments for which linearity is a good assumption, other catchments for which it's not. In general, let's say that it's not satisfied, of course, because linearity is something that really doesn't belong to hydrology. But still, it's an assumption that may be reasonable. And it was basically introduced because it makes the problem very easily tractable from a mathematical point of view. And in the past, you know, they had to make any computation by hand, and therefore, you know, they tried to simplify the problem. Okay, so let's now forget about Torricelli's law and let's continue with this linear assumption. And now what I would like to do is to integrate this equation with a mathematical proof that it's easy, but given that I will ask you to remember it, because I think it's a good question for the exam, and just pay attention because it's easy, but you know, it's something that anyway, when it has to be explained, it requires some careful attention. So first of all, we can combine these two equations into one, because I can substitute in the first equation, I can substitute W with the value of Q that is given by the second equation. Okay? And keep in mind that when you, in a problem that is described by two equations, you reduce to one because you substitute the second equation into the first. You have to be aware of what you are doing. You are eliminating a variable. And therefore, because, of course, if you had two unknowns, you needed two equations. If you find a technique, a strategy that allows you to eliminate one equation by still describing the problem, it means that you have reduced the number of unknowns. So be careful. If you eliminate an unknown, try to eliminate the unknown that you are not interested in, which is the state variable here. If for some reason you are interested in describing the storage instead of the outflow, then you shouldn't eliminate the storage. If I go by substituting in the first equation for W with this second expression, I am eliminating W, which is fine. And, you know, it's fine because I don't need to describe W. Okay? So let me make this change. So you will see that W disappear. Pt minus Qt is equal to the derivative with respect to time, the total derivative, of K times Qt. Okay, and let's continue with this one. With no more storage. Okay, good. So, first let me separate the variables and let me write Pt is equal to Qt plus the derivative with respect to time of K Qt. And for simplicity, let me divide everything by K. So I can write 1 over K Pt is equal to 1 over K Qt plus derivative with respect to time of Qt. Very simple so far. Now, in order to be able to integrate this equation, because, you know, I am interested, again, in Q, and Q is compressed into a derivative here, so I need to integrate this equation. And in order to integrate it, it's easier if I multiply both left and right hand side of the equation by e to the power of t over k. Why I'm doing that? The reason you will understand in a moment, because you will see that by This is just a constant. Keep in mind that in general, in a problem like this, t is defined. I want to know the river flow at a certain time. And then I may change this time. I may apply the model several times, but t is something that is defined by me. Like, I want to know the river flow tomorrow at noon. So I apply the model for this by fixing time. And then if I want to know the river flow tomorrow at 2 p.m., I will apply the model again with another time. So basically, this value e to the power of t over k is a constant in a model application. Okay, so let me multiply both sides, which is equivalent to e to the power of t over k that multiplies 1 over k qt plus e to the power of t over k, which multiplies the derivative with respect to time of qt. Good. Now I can compute the integral, and to compute the integral I need to compute the integral for the left-hand side and the right-hand side. Now, if I compute the integral, what is the reason why I am computing it? The reason is that I want to sum any single dq, any single increment of river flow from when? From a time 0, which is typically the beginning of my simulation, so I have to fix it. It's a technical information. So from when I want to start running the model, okay, we know this time because it's